and then I'll proceed. What are like kind of the nowadays challenges with the superconductivity? What is high temperature superconductivity, and how is it important in a way, or what are the issues, current issues associated with this phenomenon? Before I proceed, I just to tell you, nowadays there's a lot of discussion about the quantum computers. And so far, the successful quantum computer, which is being built in a hardware that is based on the superconductivity qubits only. So this phenomena is generally very important because you would understand it later. This is more like an introductory class, but once you start to get the classes on quantum mechanics and so on, you would understand this is one of the macroscopic quantum phenomena. And devices based on this would be really, really useful for the quantum computing. And as I said, in fact, the first quantum computer which is being built or are currently considered to be built, they are based on the superconductivity qubits. Okay, so I'll start like a kind of a brief introduction about this phenomena in general, and then I'll proceed. So you all know this is me. I mean, the word consists of super and conductivity. So what is this super? What do you understand by super? I would make
extreme.
Sorry?
Extreme.
Supreme.
Sorry?
Extreme.
One by one, maybe.
Like Superman.
Yeah, Superman, fine. Other words?
Supreme.
Extreme.
All these were like supervisor, superintendent. I mean, there are these for superstar, supermarket, even supercomputer. We nowadays use this word also, super glue, superpower, supermodel, of course, and then of course, I mean,
superposition.
Superposition. Yes, there are. Yeah, and of course, as you know, that in 1920s, this word, the most famous, I mean, prefix used for this as a prefix, it was used for the Superman. I mean, you know, champion of good, defender of the helpless, and then you see like you know, our Superman. So why then? But why is it different? I mean, like super. What actually do we mean when we say super?
Not ordinary.
Not found in rare conditions. Not found in ordinary conditions. Sorry.
Like not ordinary or not found in ordinary conditions. Something which is kind of completely different, qualitatively different. There is something like in one case some properties you can enhance like in quantitative way, but it's qualitatively different, something out of the world or something like that. That's what you can say about the super word as such. You know, qualitatively different from the, you know, you use it for man. Superman would be something which would defy the gravity, and yeah, all the natural laws would not imply for the Superman, for example. So this concept is something completely different. And then of course, okay, yeah, so for the superconductivity, I mean, you know that let me see, wait a second, yeah, I have to find sorry, I think I'm going back and forth. So in normal, I mean, conductivity, what we mean here is the electrical conductivity, not the thermal conductivity. We are talking here about the electrical conductivity, and usually we can define these materials from the in two, or you can put it in three categories. All the materials can be categorized in 2-3 categories based on their conductivity. One is metal, second semiconductor, or and insulating materials. So for this metals, usually if you change the resistance, or let's say if you change the temperature, resistance would change. And how does it change? As you decrease the temperature, the resistance would also decrease. And for insulators or semiconductors, if you decrease the temperature, the resistance would increase. Again, I'm talking about the electrical resistance here. And I assume that you know about the relation between the resistance and conductance, or resistivity and conductivity. Okay, that's what I'm already assuming. So the black line would mean these are metals, and this pink line would represent a semiconductor or insulator. The behavior is usually like has a certain kind of a temperature dependence. Like metals, you can observe that it's not really linearly decreasing. There is some non-linearity.
Sorry to interrupt. They're not visible.
What is not? I mean, you cannot see my.
Your screen is visible, but your slides are not moving. It's still stuck on the first slide. Okay, now it's good.
Oh, okay.
Now visible, sir.
Okay. So I'll just
on my screen.
like that's what I was presenting. Then this Superman, and then now I'm coming over here. So the problem would be, I think, let me. What it is? Wait a second.
Now it's fine.
Yeah, but wait a second. Let me just stop for once, and then. Just wait a second. Share the screen, maybe. Then I go over here. Now, is it like visible?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Now change to metal. Is it also now clear?
Yes,
If
sir.
Okay. So this black line represents the metal, because the resistance or resistivity would decrease as a function of temperature if you decrease the temperature. But this and for an insulator or semiconductor, the resistance would increase if you decrease the temperature. Now you see the dependence is not the same. Both are non-linear, but there is a certain kind of particular relationship for the metals as a function of temperature, and insulator that is completely different. And you would also study in detail about these properties. Why is it like exponentially? Usually in the case of insulator or semiconductors, it increases exponentially. And metal, it has some kind of a polynomial dependence. So, but qualitatively, that's the difference. And I think I can assume that you know what is the difference. Why the metal's resistance decreases as you decrease the temperature, and why is it so that resistance of an insulator increases as you decrease the temperature? What is the reason?
So in metals, the collision between the electrons and due to increased motion, the number of collisions increases, and thus the resistance should also increase. However, in semiconductors and insulators, the electrons actually get excited, which causes the conduction band to actually increase.
You are right. In case of metals, there are already electrons in the conduction band. Okay. That does not, the numbers do not change significantly as you change the temperature, but what it changes is the vibrations of and that's what we assume, that these electrons are flowing through a background of the static remaining ions. And these, at a finite temperature, these ions would vibrate from their equilibrium positions, and these vibrations, there is a scattering of these free electrons from these background ions. And this scattering would increase as their vibrations increases as you increase the temperature. So resistance increases as you increase the temperature. In case of insulators and semiconductors, usually this number of free charge carriers which can move around within the system increases as you increase the temperature. They go from the valence band to the conduction band. Okay, that's the major difference. Now this now we can find another category which we call it superconductor. And what it happens, I mean, I'm putting it in general, like this temperature is scale for I mean, there is a reason I didn't put the units over here. It's, you can assume it to be like arbitrary units. That's what we can define it for time being. Okay. But usually, I would say it's more relevant if we take this temperature into the Kelvin units and resistance into the ohm. Okay, that's what you can assume. Now, in this range, particularly this range is very important for 20, I mean, this 20, 10, 40, 60, 80, this Kelvin. For semiconductors, usually the resistance would decrease as you decrease the temperature, and at a particular temperature, this resistance of the superconductor becomes, what is it? What happens? Below a particular temperature, the resistance is
Zero.
Very
Huh?
close to
Zero.
zero.
very close to zero or zero.
Very close to zero.
Very close to zero.
It's not zero. Is it zero or it's not zero?
No. Not zero, but
Comes
very
very
close.
like limiting zero.
Limiting to zero. Okay. Why do you say so?
Because actual zero conduction is actual zero resistance is practically impossible, because if zero resistance happens, the current will actually stop flowing because the voltage drop won't happen.
Okay. Actually, I mean, that's what it is known, and we know right now for now. I mean, we know. And any other idea? I mean, just okay. Anyone else? If someone wants to say something, whether it's 0 or 10 to 0.
Sir, I think resistance is randomness and current brings uniformness to the randomness.
Mm-hmm.
So current will flow even if resistance is 0, because resistance is like the more the randomness, more the resistance.
So whether it's 0 or not, I'll come to all these issues like current flow.
It can be 0.
Approaches to zero.
But for semiconductors, sorry, superconductors, whether it's 0 or not.
Sir, it can be 0.
It's
Yes.
0. It's
Huh?
0. It's exact 0 for superconductor.
Sir, it will become exact zero at 0 Kelvin temperature, which is impossible to achieve. However, as we approach 0 Kelvin temperature, I feel that the resistance will limit to 0.
Yeah, that's what I heard. Anyone else?
Even above F0, it's 0.
So even above 0 Kelvin.
Just
Sir,
like
it
near.
is easy to align the moving electrons. So sir, if the electrons are already moving, which is a finite temperature, very low temperature, so sir, at that point it is easy to align all of them, so 0 resistance is possible, I think then.
Okay, so okay, fine. I'll say what it is. So far we know that it's below this critical temperature. That's what we know it. This TC, it's absolutely 0. Okay. The resistance of a superconductor is 0. But the question is, and there are ways you can flow the current, and if current starts to flow, because as you said that there is no resistance and there is no voltage drop, so current would, if you somehow can start the current, then current would flow for infinite time. Okay, it won't stop, it won't decrease. In usual case, if you take a piece of wire and you set up current in a loop, and it would kind of start to decrease and would go to 0. But in the case of superconductor, the current is absolutely 0, and resistance is absolutely 0, But the problem is, how can you conclude that? How can you say that?
Sir, when there is no rise in temperature of the current carrying wire or whatever we are using, so there is no energy loss. So resistance has to be 0.
Yeah, there are other issues. Once you see, the point is that when you what amount of the current would you like to flow? I mean, you can already, you probably already know, and you can assume that what could be the applications of this superconductor. One of the applications could be that you can transfer the electricity from one place to another place without any joule heating, which you are talking about, okay? Without any,
Loss in energy.
without any losses, the energy can be transferred from one place to another place. That is one possibility, but there are, of course, issues with it. Issues are as such because these superconductors, this phenomena is observed at very low temperature. That means you have to keep the materials at very, very low temperature. So that also costs, energy, and that also, economically you have to look for the viability of this option. So this is one of the application. And of course, because since it's a very low temperature, how much current do you would like you to flow into it? There is another problem, and there is another application which you can think about. What it is? What other application can you think about it? I mean,
Sir, I had this one doubt, confusion, you can say. Sir, you must be knowing about Lenz's law. So, sir, how will the electrons reverse their flow in Lenz's law in a superconductor?
I'll come to that. I'm coming to that. This is precisely the thing which I think I'll discuss in the next few slides. Basically, Faraday's law and associated Lenz law with it. How would it respond? But what is the kind of other application do you think from the superconductors? Except this transfer of energy from one place to another place without any heat loss.
Sir, as you earlier stated, we can use it in computers.
Yeah, that is nowadays that is more like phase and all the things which I will discuss further. But there is another important application.
Magnetic levitation, sir.
Sorry?
Magnetic levitation.
Electromagnets, like we can create.
Lenz's law and all these things which you are talking about, that's where it comes into the handy about this magnetic levitation is one of the things. But before that, there is very important application, and which is actually viable, and that's where it's widely used. Still, it's in the used everywhere. One of the important application is fabrication of high field magnets, because in the magnets, if you have to create a magnetic field, you have to flow usually the current through the current wire, and you can make the coils and Helmholtz coils and so on, and you can create the magnetic field. You can increase the number of turns, but essentially, if you have to increase the magnetic field, you have to increase the current into it. And the problem is, even if you use copper, highly conductive materials which are available into the nature, still there is some resistance. And as you increase the current, the heat losses increase quadratically. Like I square R way. So this is a problem. And as you go higher and higher magnetic field, you need cooling. Still, it's done, but usually beyond, let's say, 2 Tesla or 2.5 Tesla, it becomes really difficult to design a magnet which can generate the field in a continuous manner. Pulse magnetic field, pulse magnetic field can be generated, even the higher, like hundreds of Tesla or something for a very short time. That is possible for it. But if you want to generate a very high magnetic field in a continuous manner, it is very, very difficult using conventional magnets or conventional electromagnet. That's what I would say. So now you can think that if we have the superconductors where resistance is 0, you can apply whatever the current you want, and still you would be able to generate the magnetic field. And actually, most of these high field magnets use superconductor. Even if you go to most of these magnetic resonance imaging, machines, they use this superconducting magnets. That is really the fact. But there is an issue there also. As you increase the current, the superconductor also, is the magnetic field is created, and then this because this magnetic field is also applied to the material which is also exposed. I mean, the superconductor is also exposed.
18 hours.
Is also exposed to the magnetic field. There is a critical magnetic, like there is a critical temperature, in the same way there is also a critical magnetic field above which this superconductor becomes a normal conductor. So you cannot go above a certain magnetic field, and that's where the limitation is. But still, nowadays we can use the magnets of several tens of Tesla, which are used in the MRI machines, and that's most of these MRI machines use the superconductor. But okay, so this is one of the application. But again, I come back, how can you measure as we say that the conductivity is 0 in normal case, as I told you that there is a scattering from the vibrations of the background ions or atoms in the solids. So normally you feel when you apply a voltage or electric field to the free electrons, you feel there is a resistance to the electrons. But this is the way normal conductors would behave. But if you have a superconductor, the current would flow like there is no scattering happening. There's no scattering. They are like flowing like without any scattering event. This is really absurd. Okay, how is it possible that the current can flow? And that's what we call it not a perfect conductor. There is a difference also between the perfect or ideal conductor and the superconductor. So it's not really like a very material with very high conductivity, or it's not a perfect conductor. It's not an ideal conductor. It's a superconductor. It's completely a different state. And it's very difficult to think even like the electrons can flow, without any, without any scattering event. There are so many. I mean, in the solids, the density of this atoms or ions is of the order of something like of 3 × 10⁻26 per meter cube, and so on. So many of the atoms are present, and if you assume that the electrons are like flowing without any resistance, this is really difficult to understand. And as I said, if you make a loop of a wire and you somehow, if you are able to put the current into it, then it will flow ever. And there are ways to do it. I mean, it's not impossible to make such a loop with some current into a superconductor. That can be done. So it will be always there. It will generate a certain magnetic field that will be there. So if you keep your temperature below the critical temperature. So this is called superconductor. Now again, this superconductivity, a bit of history. Superconductivity was discovered by Kamerlingh Onnes in 1911. Onnes called it supraglider in Dutch. Literally, it means superconductor. Okay, that's what it means. Supraglider means superconductor in Dutch. I mean, in English, it would mean superconductors. The Onnes predated, I mean, it was in 1911. You can think that even Superman, the name Superman was given in 1920. So it predated, the Superman by 1 decade, but the spirit was same. like Superman does not follow the laws of this nature, like gravity, and superconductor does not follow the usual laws of electricity. Not only electricity, but you will discuss also thermodynamics. So superconductors were not just a better conductor of the electricity, they were completely different, like out of the world, mysterious, strange, like Superman. Okay. So the superconductors are actually the Superman of the in the family of conductors. Okay, now this is he received Nobel Prize in 1913, 2 years after this discovery, for his investigations on the properties of matter. It was not written like superconductivity in his citation. It was for his investigations on the properties of matter at low temperatures, which led Rayleigh to the production of liquid helium. This was more essential, actually. He was actually a low temperature scientist. He was he was the first one who could liquefy the liquid helium. The liquefaction or boiling temperature of liquid helium is 4.2 Kelvin. That is a completely different, I think it would be kind of unrelated, but that is also a very interesting story which led to the discovery of liquid helium. It was intentionally done. I mean, there were several groups which were looking for the liquefaction of the helium. That was one of the major research problem of that time, because most of the other gases were liquefied, and helium was very curious case as such, because helium, as you know, is an inert gas. So it was important whether it would have certain, whether it can be liquefied or not. It's really an ideal gas or not. These were the questions, because if it's a really an ideal gas, there is no attraction between the atoms of this helium, then it would not get liquefied. But as it came out the cases, from the problem was posed by the van der Waal, which from that we know the van der Waal forces and so on. This problem was there, whether helium could be really liquefied or not. So that was one of the problem, and he was the first one who liquefied the helium. So that means he had the availability of the low temperature in his lab. After that, the idea was, as some of you already told me in the beginning, that it was interesting to look if you approach the close to the absolute temperature, what would happen? We know that for the metals, this resistance decreases. For the insulators, it increases. But for the metals, the idea was, what would happen if you go to the very, very low temperatures? I mean, okay, that's where this is the kind of the scale, just to give you the idea about it. Helium boils at 4.2 Kelvin, hydrogen boils at 90 Kelvin, 70. So most of these gases were already liquefied, and it was like helium. So, but he was working on the liquefaction, and then he started to work, how the electrical resistance of different materials behave at very low temperatures. Once, because he has the availability, then he started to work on this another problem where to study the electrical resistance of metals at very low temperature when you're close to 0 Kelvin. But he didn't expect it. Of course, he observed it, he reported it, but he didn't expect the superconductivity. And it was observed in, as I'm saying, mercury. And that is also another interesting aspect of this discovery. Why mercury? So once it was discovered, it was not understood for a very long time. As we will say, I will discuss about that. So the idea was, there were three models at that time: this Kelvin, Mathiasen, and Debye. So there's different models explained in a different way. They said, as you decrease the temperature of the metals, of course the resistance decreases, but below a certain temperature, Kelvin proposed that it would start to increase the resistance because electrons would start to kind of freeze. I mean, they would start to freeze. They would not be able to move as you go down to very low temperature. Mathiasen said, okay, there would be always a kind of a background resistivity or because of the presence of different, and that we still know that that is actually true because of the very small impurities or scattering from the very small impurities or the defects and so on. Whereas Dewar proposed that as you will go to zero towards, as you, I mean, you said it, as you tend to zero, the resistance would also tend to zero. It would not be zero. It would be an impossible case, like you were earlier saying, that as this would be only like it would, if you would tend to 0 Kelvin, your resistivity or resistance would also tend to 0. And that's where, that's where Ohms also started to work on this problem. And first he tried to get it for different metals. But the problem was always, there was always some impurities in these metals. And it was very difficult to get ultra pure or very highly pure metals. Because once they are there, they are there. It's very difficult to reproduce it. Then he chose the mercury. Mercury is a metal, but at room temperature, it's in the liquid form. This is also a very interesting case. This is one of the metal which is in the liquid form at room temperature. So it was easier to distill it. So make it more I mean, for the purification point, it was easier to do the distillation of the mercury because it was already in the liquid form. And otherwise, all other metals have very high melting point and vaporizing points. It's I mean, very, very, very difficult. So, but for the mercury, it was easier to do it. So he used this mercury, and of course, that I mean, the experimental setup to measure the resistance was also challenging, but that can be done. Still, we do it. And what he observed that exactly at 4.2 Kelvin, the resistance drops. And he said, okay, there is a very fast drop. Then first, okay, as a a good scientist, because he was of course a good scientist, he tried to reproduce. First he thought, okay, there is some kind of a short circuit that must have happened. But after the repeated experiment, the transition happens exactly at the same temperature, and it went from the let's say 0.125 to some value. But what is this value? How do you measure? Actually, you cannot measure. It's really 0. This is also true. I mean, how did he reach to the solution, the conclusion that it's a 0 resistance? This is another story. But in this kind of measurements, what you do is you flow the current, you measure the resistance by measuring the voltage across the resistor. And if it has to be a 0 resistance, the voltage across this resistor would be also 0, and you cannot measure the 0. Your measurement device would of course has a certain sensitivity value, or say least count, below which you cannot measure. Just a second, I need to take this call. Just give me a second. Yeah, sorry. Okay. So this is always a problem, that how do you measure such a 0? I mean, your voltmeter would have a certain least count. Your even your meter scale would have a the lowest sensitivity or the least count below which you cannot measure. And in fact, he was able to measure till 10 to the power minus 6 ohms, because each voltmeter would have certain least count. Cannot have 0, or you cannot measure the 0. In the same way, you cannot measure the infinite. So he was, of course, he designed the experiment slightly in a different way. he prepared this kind of a wire or a tube which would have this wire, and he put the first it was in the this in the normal state, and then he put like you can put a magnet. Some of you might know this kind of a design from some earlier experiments, a magnet from a thread, and through this thread a mirror is attached, and if you reflect the light from it, as soon as there is a current in the wire, there would be a magnetic field would be generated by this wire, and there would be a torque on this magnet, so it will move, and the spot on the wall would move. So you can generate what it is. You go into the superconducting regime below 4.2 Kelvin, you put the current into it, and then you put it in a persistent mode. That persistent mode, that if the current is flowing, it would keep flowing inside it. You switch off the external power supply. There is a way to do it. I mean, I'm not explaining it right now, but there is a way to it. You can take out, you can make a continuous loop, so the current would keep flowing. Now there is a certain magnet. Yes.
Sir, I watched on Discovery that they were telling that superconductors hate magnetic field, and they will produce current on their own too, so that they can prevent magnetic field and make their own.
That is something else. I mean, this is like inside the superconductors, the magnetic field cannot penetrate. Okay, and there is again a certain magnetic field once they start to penetrate. There are different ways, like type 1, type 2 superconductor. I'll come to that. So the ways it interacts with the magnetic field, but it of course generates. The one thing here is that they would generate the magnetic field, and this magnetic field would produce the torque on this magnet. And then that's what. Or do you want to ask something else? What is the question here?
Sir, they were talking about Maglev, which is the flying train in Germany.
Not in Germany. They already demonstrated in Japan actually a few years back. I have a video also regarding that. If you want, I can show that later on. This train was tested, and this is possible to have this effect. This is something called the superconductors are perfect diamagnets. That's what we'll come to that. Okay, but here, as you see, that if it's in the superconducting state, you take it to the superconducting state, then there will be a torque, and this light would have a certain reflection at a certain point on the wall, like this. Now, if it's moving in the persistent mode, that means it's moving in a loop, and it's not changing, then the magnetic field produced by this loop would not change. Hence, the torque on the suspended magnet would not change, and that means the place of the spot on the wall would not change as a function of time. If the resistance of the superconducting wire, it has the finite resistance, then as a function of time, the current would start to decrease. The magnetic field produced by this wire would decrease, and hence the torque would also change, and as a function of time, the spot of this light would start to change. And that's what he actually first detected it. It's kind of increased the sensitivity of the way to measure the resistivity in an indirect way. So he measured it, I think, for months and so on. There was absolutely no change in the spot, and that's where he realized that, okay, from there he concluded that otherwise it would have moved. This spot would have moved, and that's where he realized that it's not really a high conductivity or something like that. It's really a superconductivity. It's something different. He could sense that. And now we know from the different measurements, you can actually have such arrangement for years, current would not decrease and so on. This is one aspect, and that's where he reported. Now, there is another thing which we were talking about based on that, this Lenz-Faraday law and so on. So if you have an ideal conductor, there are two ways. You have an ideal conductor. Forget about right now about the right part. Just think about this left part of the screen, which says ideal conductor. So let's say on the green, on the leftmost part, you have a ideal conductor. That means there is no resistance. But ideal conductor, if you, let's say, you apply the field first, that means downwards time, you apply the field, so the field lines would penetrate it. Then you start cooling it, and field lines would still penetrate because nothing is changing, okay, in the superconducting state. So this light green at the bottom one represents the superconducting state. You start cooling, it would be a superconductor, but nothing would change. Line would still keep penetrating because you have not changed anything. If you now switch off the field lines would, of course, there would be a, currents would be generated inside it in an opposite way, and that would generate the magnetic field just in the opposite way due to the Faraday's law. In the same way, for if you first cool the material, that means you make first the superconductor, then you apply the magnetic field. Of course, because there are free charge carriers, because of the Lenz's Faraday law, the current would be generated inside the because of the change of the field, because del B by del T. Because field is changing, there would be an electric field inside it, and that would be the currents inside this ideal conductor would be generated, and the direction of the currents would be determined by the Lenz's law in such a way that it would oppose the external field. So inside the field, it would be like it would generate the internal field in opposite direction, so the total field is zero inside it. So this is the idea about the ideal conductor. But what is the difference in the superconductor? In the first, and in this case, when you first cool and the magnet, like now we are discussing about this right side part, upper part, that is fine, it's still fine. You have cool, you apply the magnetic field, the currents would be generated inside it in such a way that would oppose this change, and it would generate the field opposite to the externally applied magnetic field. That is understandable. But what is different from an ideal conductor is that if you apply first the magnetic field and then you do the cooling, you observe the same effect, which is you cannot understand from the Faraday's law, because you are not changing anything except changing the temperature, because you are not decreasing or changing the field. Even if you first apply the magnetic field, so the field lines are penetrating this conductor, and then you cool it, the field inside the superconductor is zero. Even if you do not change the external magnetic field, as soon as you go into the superconducting state, the currents are generated in such a way that the magnetic field inside the superconductor is zero. So that's what we call it, a new thermodynamic state of matter, and that's why we say it's not very, a normal state as such. Okay. It's completely or something which is entirely different state over there. New thermodynamic state of the matter. That's what we, if you think to call it. So it's something absolutely different. It's not, you cannot explain from the normal, laws of the conductivity. You cannot explain it from the laws of electrodynamics. So it's something which is entirely different state, and that's where this property is actually used to generate the magnetic levitation. Because for a superconductor, of course, there are changes of deviation, but this susceptibility, magnetic susceptibility is -1. That means it's a diamagnet with a susceptibility of 1. It's a -1. In fact, it should be like -1. So this is a normal type 1 superconductor. That's what we call it. Like field does not generate, do not penetrate. But of course, if you increase this field above a certain value, then field would start to penetrate inside the superconductor. At the same time, it also becomes normal conductor. But there are type 2 superconductors. This magnetic field can penetrate in a certain way that field still can penetrate, but still it can remain the superconductor. In certain regions, it would be this would be kind of a mixed state. That's what we call it, a mixed state.
Sir,
So
I have a doubt.
Yeah.
Sir, if the magnetic field is changing,
Mhm.
so sir, the conductors will opposite. So the electrons will have to change their motion.
Yes.
So
Yes.
sir, in a superconductor where there is no resistance, who gives the energy to change the motion?
I mean, that's what we said. I mean, okay. Think about it in this way. Magnetic levitation is possible in normal conductors also. In Faraday's laws, as soon as you change the magnetic field, that's how you generate the electricity. In usually in inductors or motors, they work on this principle that you move it, the shaft of a magnet, and electricity is generated. So who gives the energy? In a way, it comes from this movement, of course, but in the superconductor there is no loss, there is no energy transfer. That's the thing. So you do
Sir,
not
but
need
movement of electrons means they have energy, right?
no,
And
you
if they are
don't.
reversing their entire movement, means energy has been given to them to reverse it.
Of course, I mean, initially, like, how do you create that could be a question, like when you have a wire and it's a, let's say, superconductor, how would you, because how would you sustain the current into it? How would you generate, because it cannot have any voltage difference across it. So you have to, this is the same way, to initiate it, you will need certain energy, and that could, of course, would be given by the energy of the moving shaft or whatever is generating the magnetic field. But once they are in the motion, they would move without any resistance. There would not be any energy dissipation inside it. But of course, to generate it, let's say you have to even generate the current inside it, inside the superconductor, initially you would need to give certain energy into it in a way that you have to connect certain material, which is a normal material, through which you can sustain the voltage and through which you have to start flowing the current. So you have to give some certain energy into it. And this is the same way. So energy would come out like normally in the turbines, or where you generate the electricity. It comes from the whatever the way, like either is from the steam or from the falling water from a fall, then that starts the turbine, and this turbine moves in a certain magnetic, the coils moves in a, either coil moves or the magnet moves through this motion of the turbine. There is a relative motion between the magnet and a closed loop, and then you generate the current into it. So this energy comes from essentially from the either steam in the thermal power plants or in the hydropower plants, comes from the falling water. That gives the energy. So in the same way here, whatever is the changing the magnetic field, or whatever once you are moving the magnetic field, that gives the energy. But here it's completely entirely different. Here that's where we call it a new thermodynamic state of matter. It's very mysterious over there. But once you flow the current into it, no way that you can change anything. I don't know.
Sir, we can conclude two things out of this, like either our understanding of electron is a bit flawed.
No, our understanding of the electron is not flawed. I would say that whatever, till you have the school education about your knowledge about the conductors and the way current is flowing, that is not complete. I would not say it flawed over there. You would understand it in a bit more. I mean, what is an electron? That is like, there are different things you would understand later, like whether it's a particle, wave, and I mean, quantum mechanically, it's a different thing. You still need to study a bit more. I would put it in this way that our knowledge is not flawed, or our information is not flawed. We know exactly what an electron is, how does it behave. But what I can say is that our understanding about the normal conductor does not apply to the superconductors. It's a kind of a different concept. That's why it's, as I said, it's not an ideal conductor. It's not a perfect conductor. It's a superconductor. It's a new thermodynamic state of matter over there.
And sir, nothing about the magnetic field lines, because they are not losing their energy, but they are transferring energy to the superconductor electrons to produce new current on changing magnetic fields.
Yeah, I mean, there would be, I mean, overall energy dissipation is less, but of course you have to spend a lot of energy to make it really keep it cool against the environmental heating itself. That is another perspective of it. You should never forget about that you have to keep it cool against the thermal heating from the background, environmental heating and so on. That requires a lot of efforts. So
it's 1830.
So there are actually these two properties superconductors must have: expulsion of the magnetic field inside it, and second thing is the zero resistance. Or so these are the two essential features of it. And as I was discussing, the superconductor, if you keep applying the field, of course, in this left one, that's what we call it type 1 superconductor, it remains in the superconducting state. That means it can expel the magnetic field. If you go above a critical field, you would reach into the normal state, so that it would become like a normal conductor. And this critical field changes with the temperature. So around the TC, it's a very small. That means even if you apply a very small magnetic field, your superconductor would change into the normal state. But if you go well below the critical temperature, then this Hc value would keep increasing. That means you have to apply high magnetic field. For this normal type 1 superconductors, actually these Hc values are really small, and that makes them really useless, because that means whatever the magnetic field you would generate, a very small magnetic field can lead to the normal state. So that means no use. But then there are these type 2 superconductors where they have the mixed state, where the magnetic field can penetrate at a certain positions in a certain geometry in a quantized flux. So this unit, I mean, lowest limit of this quantized flux is 2.07 into 10 to the power minus 6. Gauss, G is Gauss, one of the unit for magnetic field, C square. I think this value is probably not correct, pi C. It's Hc, I think Hc by 2E actually. That's what the value of this quanta of the flux is. We call it a quanta of flux. And that means this can happen either this value or multiple integer of this value, and can penetrate and penetrate at a certain locations. So where this magnetic field penetrate, the material becomes normal, but other places it still remains the superconductor. So it's a kind of a mixed state of both superconducting as well as mixed state. And even if you keep increasing above another Hc2, that means critical field 2, it would turn into the normal state. So usually this type 2 superconductors, this Hc2 values are very high. So these type 2 superconductors are actually used to make high field magnets, because they can sustain up to very high magnetic field, but still you have to cool them to very low temperature. And that's where usually in MRI machines, this liquid helium is used to keep this superconductors below a certain temperature. Okay, now comes the theory. As I said, although it was discovered in 1911, it really took long to understand how does it behave in this superconductors. A lot of people even still believe that this is not a correct theory, but of course it was like proposed by the Bardeen, Cooper, Schiffer in 1956. a theoretical description about this or theoretical understanding about this superconductivity, which also led them to win the Nobel Prize in 1972 for their jointly developed theory of superconductivity called BCS theory. It's called BCS theory, Bardeen, Cooper, Schrieffer in 1956. I would briefly explain what it is. So it's what they tell is, but between electrons, usually they start. I mean, both are negatively charged electrons. If you bring them close together, they would repel each other because they are both negatively charged. But they can form an attraction. This a weak attractive force can be formed in the electrons by electron phonon interaction. I have not introduced the word phonon so far. This phonon is actually related to the vibrations of the background ions over there. These vibrations also can be quantized. The way we quantize, I mean, vibrations, of course, would be related to the wave. And the way we can quantize electromagnetic waves into the photons, we say there are photons of this bundles of energy. The same way these vibrations of the back atoms inside solids can also be quantized in terms of something called phonon. And through this electron phonon interaction, they can form a bound pair of electrons. So two electrons can form like a pair which are bound and with opposite momentum and spins. And these pairs of the electrons are called Cooper pairs. It's something like that electron comes, and due to this electron, because there is a positively charged background of the atoms, this at a particular location, they would start to attract towards this electron in a certain way. And since background ions are heavy, this electron which is moving, that can go away. Meanwhile, they would still be, deformed. The lattice would be deformed, and they would form a kind of a field which can attract another electron. And these two electrons, which primarily causes first this deformation of the lattice, and the second electron, they can still get bound, or they can by this deformation of the lattice, which causes the phonon. So this is called something called electron phonon interaction. So this two electrons can be bound via this electron phonon interaction, and these two electrons are kind of can move in a phase with each other. So they would, it's like getting the information about through this electron phonon interaction, these electrons can get the more information about the positions of the atoms, and they can kind of avoid. That's what, in a very naive picture, I can tell you that they know kind of the position, these Cooper pairs know the positions of the electron, and they can always avoid this collision with the ions and so on. They can move it. So they kind of form a pair. So now just some information. The different materials with different TC. Niobium TC is 9.5 Kelvin. Lead TC is of 7.2 Kelvin. Tantalum 4.2 Kelvin. There are some alloys with different TC values. Niobium nitride, niobium tin, niobium germanium, which has 20 to 25 Kelvin. And these are actually the materials which are really useful for the practical application. These kind of alloys. And this is the table you can also find on the web that this green, blue ones are the one which can form the which are the superconductor at ambient pressure, and these are the green ones. You have to apply more pressure to make them superconducting, and this rest of the white ones are never superconducting. So you can directly see now this better conductors, or say materials with high conductivity like gold, silver, copper. They are not superconductor. They do not become superconductor. And because in this materials, this electron phonon interaction is very weak, and hence they do not form the Cooper pairs to the detectable temperatures, even after applying the high pressure. And again, there is you can find another interesting thing although iron is there is an exception there, but another like cobalt, nickel, iron, these are three magnetic materials. It does not, cobalt and nickel, even iron in ambient condition do not form the superconductor. I mean, they do not undergo to the superconducting transition. So very material elements with very high conductivity and the elements with the magnetic properties avoid the superconductivity. This is the kind of observation you can make from this table directly. Of course, for this ideal gases and so on, it's also very difficult. So because their interaction is very weak, and there are different reasons for that. So, but other blue elements are superconducting. And Ben Mathias gave kind of he was a famous scientist who discovered a lot of these alloy superconductors. Okay, he was a pioneer in search of this alloy-based superconductor, which are still used. So he gave the 6 rules. I have stated 5. I will put it 6th one also here. So materials with high symmetry. High symmetry means crystal structure. Symmetry of the crystal structure of the materials should be high for a superconductor with a reasonably high critical temperature, because you want a superconductor with high critical temperature, high density of states, electronic density of states. You would, I think, study a bit later. Stay away from oxides. So oxides, he said, oxides are not superconductors. Stay away from magnetism and stay away from highly insulating materials over there. So these were the rules, and you can start to mix it, and then you can find a good superconductor. And his 6th rule was stay away from the theoreticians. What he said, theoreticians can explain. They could explain after like almost 40 years or 45 years about the superconductivity, but they could never predict that this element or this material would be superconducting. They can explain it later on. So that's what he said. This would not give it, but all his this 6 rule, I mean, okay, at least 5 were wrong. When in 1986, Carl X. Mueller and Bednorz discovered superconductivity in a material in this given by the red one around more than 30 Kelvin, and soon the materials with very high critical temperature were discovered, even high than the boiling point of liquid nitrogen. Earlier, you have to go to lower temperatures below boiling point of liquid nitrogen temperature, which is 77 Kelvin. That means you had to use the liquid helium for most of your experiments or there, which is scarce, which is costly, but generation of the liquid nitrogen is not that much costly, because first of all, the availability of the nitrogen in the environment, and the process is also rather simpler over there. So you can easily generate. So the critical temperature of some of these materials was even higher than the liquid nitrogen temperature. As soon as this lanthanum, this Carl X. Mueller and Bednorz, they discovered the superconductivity in this lanthanum barium copper oxide, which was above around more than 30 Kelvin or 40 Kelvin. By that time, it was established by the BCS theory that the highest critical temperature could be, I think, around 24 or 25 Kelvin. There could not, superconductivity cannot, that's what BCS theory told us, that superconductivity cannot be, the critical temperature cannot be above 25 Kelvin. There was a limit. So this new discovery and the superconductor defied all the established theory, as well as all the rules of the Mathias. And because these materials were oxide, their parents compounds were magnetic, they were not really symmetric in a way, did not have very high crystal structure, symmetry with very high symmetry in the crystal structure, density of states, and so on. All these rules were defied in this discovery of the high temperature superconductor. And of course, Mueller, it was, I think, in 1986, and the next year they also, I think it was the same year or next year, they received the Nobel Prize for that. So do you want me to continue about this background high temperature superconductors, or do you want me to stop and we want to have another class on this?
Sir, another class.
It depends on which day you want to take the class.
Sorry?
Sir,
How?
it depends on which day you want to take the class.
You can, because this is now over. So if you are interested, you can write me. You better would be before 4th, because after that usual classes would also, my another classes would also start. So I would prefer before the 4th, and you can let me know the time if you are interested, and the date and time. I would need the date and time.
Yes,
We
sir,
can.
we will.
I can finish this part, and then we can have a discussion also if you would like.
Sir,
So anyways, on Monday we have a class from 4 to 5 for this intro to EPH, so we can finish it then and then.
But is it? I have to talk to Professor Lalita Sharma. Is another teacher assigned to it, or already, or for that date?
I don't think so. I don't think so. Anyone has been assigned yet. You can inquire. Actually, like previously we had Ajay Vasan sir, and instead of taking